Hello everybody and welcome to part 9 of the Python for Finance tutorial series. This one is covering portfolio optimization and I want it to be a bit more different. So I'm going to start from the end. What we see on the screen is basically our end result. This is what we're going to create during this tutorial. And if you want to know how it's built from scratch, then feel free to watch it until the end. Now, when we mention portfolio optimization, basically what we mean is we have a portfolio of specific assets and we're optimizing the allocation of our resources among these assets to achieve a certain objective. Now, if in this case we have an objective to find the portfolio of those assets that has the lowest risk, well, we get a specific weight of our portfolio towards each asset. So if you take a look at this particular example, I have 7 assets, 7 companies to invest in. And these weights, so 8% investing in Bank of America, 0% in Tesla, 52% in Coca-Cola, and so on, creates the optimal portfolio for having the lowest risk in my portfolio. Now, if my objective is to achieve the highest return, then you will notice that our weights have changed, even though that we are using the same companies in our portfolio. So we have 0% in Bank of America, 57% in Tesla, 1% in Coca-Cola, and so on. And if we want to make sure that we have a nice, let's say, ratio between the two, then we are going to use a sharpe ratio, which is comparing the return that we expect to have with the risk that we are taking. And this ratio is called sharpe ratio. And if we want to achieve the highest ratio, then we get a completely different portfolio allocation. Now, this visualization on the right side and the way it's created is basically a Monte Carlo simulation. We have, in this case, it's 7 companies, but it's not really limited to the companies that you can take, or if you want, you can also include cryptocurrencies. It's just creating various random portfolios containing these assets. Now, as you can see, there are, on the x-axis, we have the volatility or the risk measured by the standard deviation. And on the y-axis, we have the return. So that's how you should read it. Ideally, you're looking for a portfolio or one of these dots that is as much as possible on the left side, so having less risk, and as much as possible on the upper side or achieving the highest return. The color map that is shown on the right side, as you can see, the lighter the color is, the highest the sharpe ratio is. The more darker, let's say, it is, then the sharpe ratio is smaller. So we're going to start with getting the data. What we're going to do is we're going to find the annualized return and the risk associated with every company in this case, and we're going to see how we're going to build this to come up with this visualization, as well as come up with all this information of what is the best allocation of our resources to achieve such optimal portfolio. So I'm going to do the following. I have some parts of the code from the previous tutorials, but I've just extracted the ones that we're going to use for this particular one. Feel free to pause the video and copy these parts in. I've selected only 2 companies, 2 tickers at the moment, so we're going to start with 2 and we're going to build and get more into our model. The period that I've used is as of 2014 until the last date for me that I have available data points. So what we're going to do is we're going to get the data using the web data reader, something that we do in all the previous tutorials. And I'm also going to create an empty data frame returns. So pd.data frame. Now, once we have the data, what we're looking for is basically the daily return or the changes per day. And we're going to do that. We're going to calculate the percentage change. Now, once we have this information on company level, what we're going to do is we're going to add it to our returns data frame. So if returns.empty, then returns would be equal to data ticker. Else, returns would be equal to returns.join data, then thicker and how is outer. So let's take a look at how this looks at the moment. So I'm going to print returns.head. Just to make sure that the script is running well, and I would suggest if you're creating a bit of a longer script, make sure that you test it more frequently, not when you write 100 lines of code. So this is the first 5 days. That's the head. We can see the return, so it looks that the script so far is working good. So we can continue with the next part. Now, if you remember the visualization, we had a lot of simulations of creating different portfolios. So what we want to do is we want to have a specific, let's say, a number of portfolios that we're going to create randomly. So let's start with 50 portfolios, and then we're going to actually let's start with 5, because I would like to show how the weight is being created, and then we're going to continue with 5, and then maybe 20,000 or so. Now what we need is we need to generate random portfolios. Now in order to do that, we're going to do the following: for portfolio in range number of portfolios, so in our range 5, we're going to generate random portfolio weights. I would like to add a comment here. I think that's useful if you're creating a bit more complex script, just to make sure that if you visit this script later on, or if someone else is looking at it, to add some additional useful information. So weights would be equal to np.random_sample, and here in brackets we're going to have len of tickers. That looks good. And if let's print this. So what I expect to see is we need to it will generate just some random weights 0 to 1. In this case we have 2 companies, so it's generating 2 random 0 to 1s. But if we invest 92% in company A and almost 92% in company B, or 59 and 62, these 2 together don't add up to 1. And that's not ideal, because if in our portfolio all the weights should add up to 1. So we need to first start and adjust that. The way we're going to do that is weights would be equal to the following. We're going to use weights divided by np.sum weights. Now what we do in this case is basically we are summarizing the 2 weights, or if we have 5 companies then it would be 5 weights, and so on. And well, let me print weights. And then we are dividing each individual to the total. So at the end, we indeed have weights coming together to 1. So the sum between the 2 is now 1. And that's more of what we're looking for. And if we add one more company here, it's going to create a weight between 3 companies that all together would be equal to 1. Now, ideally, what I want to avoid is having a lot of decimals, because at the end I would like to take a look and make sense of the data, and I would round this to 2 or 3 decimals. So this is in percentage, so that's 26, maybe 26.6 is sufficient. So I'm going to do that as well. So weights, here I would create np.round, and I'm going to round this. Let me add this like this, parentheses, and then let's create 3. So 3 decimal points, and ideally what we want is we want all these portfolios to be stored somewhere, so then later on we can take a look at the portfolio with the lowest risk, the highest return, the highest sharpe, but also what is the weight. In order to do that, we need to create empty lists and then add all this information there. So what we're looking for is portfolio returns, portfolio risk, sharpe ratio, and portfolio weights. All right, that's much better. So next we can continue with, first let's actually add portfolio weights.append weights. I will take a look into what this means for these 5 iterations of the simulation. Then we're going to calculate annualized return. Now, annualized return is equal to np.sum returns.mean multiplied by the weights, and then multiplied by 252. Now, what does this mean? Well, the returns, what this variable contains, this data frame contains, is basically the daily changes, the returns of the companies. If we take the mean, it's the average return, but we also want to apply the weights that we've randomly generated. And in order to get the annualized return, we need to multiply it by 252, which is the average number of working days in a year when it comes to stock exchanges. If you're using this for cryptocurrency, you need to set this to 365. Then we're going to append this to our portfolio returns. So we're going to append annualized return. So far, once this runs, when it starts iterating, we're going to generate the weights. It will be added in our portfolio weight. Then it's going to calculate the return. We're going to have that in our returns. Next, what we need to do is we need to calculate, let's say, matrix, covariance, and portfolio risk calculation. Let's make this a bit higher. So what matrix covariance is basically creating a matrix of the covariance between the stocks. And the way to do it is we calculate returns dot covariance, again multiplied by 252 in order to get the information for a year. In order to calculate the portfolio variance, we need to use a formula np dot, which is actually a product formula. We need to use the weights, transpose them, then np dot matrix covariance and weights. If you're familiar with finance and if you've studied this before, you should know that returns, if you want to create a sharp ratio, you need the standard deviation, and in this case we have the variance. So we have to make sure that we have the portfolio standard deviation, and the relationship between the two is the variance is actually standard deviation squared. So portfolio standard deviation is equal to actually the square root of the variance. So np dot sqrt of portfolio variance. And this is our measure for portfolio risk. So portfolio risk dot append portfolio standard deviation. Now, so far what we have is we have generated the weights, we've calculated the returns and the risk. What we need to do is we can also calculate here the sharpe ratio, which is equal to the... Now, here you need to know that you can do annualized return divided by, return divided by the portfolio standard deviation. But if you want it to be let's say 100% correct, you need to adjust this return for the risk-free rate, because you need to, basically this ratio would be the additional return that you're taking over the risk-free rate, and you need to divide it with the risk, because otherwise the risk-free rate has no risk. And if you want to have a more accurate measure, you need to do annualized return minus risk-free. Now at the moment we don't have risk-free, so I'm going to add it up here as RF is equal to 0. If you want to adjust it later on, if you have information on the risk-free rate, again that depends on the countries as well, that's how you can do it. So this sharpe ratio we're going to append to our empty list. Sharpe ratio is equal to dot append sharpe ratio. Maybe this should be portfolio risks ratios. Let's do it like that. And now let's actually let's just run the script as it is, just to make sure that we don't run into any error. But if we do, oh wait, is not defined. That's on a line. So if you run into an error, that's why I would like to check the script. You can always read information on where that error is. So line 42, if you want to go straight to that line, you can use Alt and G, and then you can just type the number and it would allow you to go to exactly that line. So in this case, what I have is I need to use weights. So it's a typo that I have, and that should solve my error, at least this one, unless we run into another one. All right, that looks good. Let's quickly take a look at portfolio returns. So we have 5 data points, which is actually what we expected, because we did 5 random simulations, so that's good. Next, we can move into combining these information to make sure that we can manipulate them in a better way. So what I'm going to do is I'm going to convert them to NumPy arrays. So portfolio returns would be equal to NP array of portfolio returns. And I'm going to do this for portfolio risks. NP array of portfolio risks. Same goes for sharpe ratios. Sharpe ratios, and I think this is sufficient. The weights, there's nothing that we can do. It's fine as it is. And I'm going to create a portfolio metrics. And this is where we're going to combine all these different lists, or arrays in this case, into one. So what portfolio metrics would be, it would be portfolio returns, portfolio risks, sharpe ratios, and weights. All right, so now we have some more some progress regarding the final outcome. We're going to convert this into a data frame. So let's create portfolio data frame, which would be equal to pd.data frame of portfolio metrics, and we're going to transpose this. And let's rename the column. So portfolio.columns would be equal to, first we have return, then we have risk, then we have sharpe, and then we have weights. And let's print this. So let's print portfolio underscore df to take a look at how this looks if we have 5 portfolios. And hopefully no issues that we run into. Oh, that seems not to be the case. Line 58. Oh, it should not be portfolio dot columns. It should be portfolio underscore df dot columns. So it's important, of course, to take a look and run the code as you go. All right, so now this looks, so it looks kind of good, but not great. What we're missing here is the weights. Because what I've added, and this is a mistake that I did, as you can see, I have weights, which is a number. So I made a mistake when I was combining these 4. And the issue here is, here, when it comes to the weights, I should add portfolio underscore weights. And that should provide me with a better outcome that I have at the moment. All right, that looks better. So we have 3 companies. This is the return, the risk, and the sharpe, and the weights of portfolio with first iteration, second, and so on. All right, good, that works. Instead, what I want to do is I want to go back to 2 companies because I would like to show something, and we're going to create 50 portfolios instead. Now we already have all the information gathered into one data frame. Now what we need to do is we need to identify the portfolios that have minimum risk, the highest return, and the highest sharpe ratio. How do we do that? Let's create a variable min risk. That would be equal to portfolio underscore df. So in our data frame related to the portfolio, maybe this should be portfolios with an s. Maybe let's do it like that because it's plural. We're going to use iloc. So we're going to locate. What are we going to locate? Well, we would like to locate a position where portfolio underscore df, so portfolios df, risk is, so first we need to check s type float dot, I can do it here like this, s type float dot id min. So what this means is it's searching first this part. So it's finding the row where we have where the risk as float is minimum, IDX min. So the row where the risk is the lowest, it's locating the same one for the entire data frame. So if it's row 50, then we get the 50, the row 50, but related to the return, risk, sharpe, and weight. Let's try and see if we print the minimum risk, what is it that we get as an outcome. So hopefully it runs 50 times. It provides us with a portfolio that has the lowest risk. Portfolios.dfi. This is the print that we ran from before. We don't need that one anymore. All right. Now, as you can see, this is the lowest risk that we have in those 50 iteration, and that's actually exactly what we're looking for. Except we would like to also have the highest return, which is equal to. Actually, when it comes to highest return, we can use the exact same formula, except instead of searching for in the column risk, we would search at the column return. And instead of IDX min, we are looking for IDX max. Simple as that. If we want to get the highest sharpe, we can use exactly the same formula, looking for the highest number, but in the column sharpe. That's it. So in few lines, we have the portfolio that we need and we would like to present. Now, let's make sure that they're printed correctly on one side, and also let's make sure that we have a nice visualization. So first thing what I'm going to do is let's have the printing part. So, and we can test that with less portfolios. So let's say lowest risk, and then we're going to print our min risk, which has all the information for the portfolio. We're going to print tickers, and I would like to print just an empty row. Then I would like to do the same for, say, highest return, and then I would like to get highest return and tickers again. And I'll show you also why I want to see the tickers, because if you see the weights, you need to have the tickers to assign them with. Otherwise, if you get just 20, 15, 10%, yeah, it's more difficult to align, and especially if it's for more companies. So there is some improvement, and that's something that you can work on to get a nice overview and connect the weights with the tickers. And highest sharpe ratio would be equal to highest sharpe tickers. I'll print them again, and just another empty one. Let's start with this, and then we can continue with the visualization part. And also we can think of what can we improve to our current model. So if we want the lowest risk, then you see this portfolio has 0.3. It's lower than all the others that we have listed here. If you want the highest return, we have a different allocation of our portfolio between the two companies. If we want the highest sharpe, then we have again a different one. And as you can see, in this case, the sharpe is 1.03. It's a bit higher than the one that we get with the highest return, and much higher compared to the lowest risk. So we can increase our portfolio size. Actually, let's do it a bit later. Let's start with 50 with two companies with 50 iteration, and then we'll do a bit of a larger sample. So this is the visualization part. First, we're going to create a figure. Let's say the fixed size is equal, let's say 10 by 5. Then we're going to create a scatter plot, and the scatter plot would have the following. We will have the portfolio, risk, so that's our x-axis, portfolio return. This should be plural, portfolio risks, portfolio returns, and then C is going to be equal to portfolio returns divided by portfolios risk. This is how I have it, portfolio risks or portfolios risk. I think it's portfolio risks. Yeah, portfolio risks. All right, so this is basically our sharpe ratio, which will be used for coloring. That's what the C stands for. plt.x label, we're going to add an x label, volatility. It's measured by the standard deviation. You can change the font size to, let's say, 20. plt.x. If you want to change the x text size, you can also do that. Font size, let's have 10 or 15. And also y text font size equals 15. And if you want to have some structure, maybe it's good to start like this. plt.title portfolio optimization font size is equal to 26. plt.x label, plt.y label, return font size is 20. Then you can continue with the x, y text. And then what we can do is, I think you can do plt.color bar and then add label to be equal to sharpe ratio. And we can show the figure. I think this should be sufficient. Let's do a bit more iteration. Let's go with 100. And here you can see that, and I think what's very important to note is that the speed of processing this information is quite high and very important. So this is our final outcome. And this is, I need to maybe either decrease the font, but make sure that this volatility part is shown well, because otherwise, if you export it, it probably would look good, but if you run it, maybe you might run into that issue. So what does this mean? Well, there are 2 points that are at the end of this line. This is probably the Coca-Cola allocation, 100% to Coca-Cola. Oh, sorry, in this case it's Tesla, so it's 100% to Tesla and 0% in Bank of America. This is 100% in Bank of America and 0% in Tesla. If you move from being 100% invested in Bank of America a bit more towards Tesla, there comes a point where your return is higher than if you're 100% invested in Bank of America, but your risk is lower. And that's actually the power of, at least in theory, the power of diversification. So since we have only 2 companies, this line, if we do a lot more iteration, would be almost filled with portfolios, because these are randomly generated. Sometimes we have empty spots. But ideally what you're looking for is what we mentioned. What is our goal? Is our goal to have the lowest risk? In that case, well, we can find this point somewhere here that has a return of, let's say, 0.21. So somewhere around here, this is probably the point where that offers us the best diversification to optimize it, actually to optimize our portfolio to have the lowest risk. And that portfolio consists of 82% Bank of America and about 18% in Tesla. Now, if our goal is to achieve the highest return, you can see that it's not 100% in Tesla. And the reason for that is because we did not have an iteration where the Monte Carlo simulation tested what we would achieve if we had 100% in Tesla. So it's not that you would increase your return if you invest in an asset that has lower return. And the highest sharpe ratio is something that a lot of people are interested in. In this case, it's a bit over 1. And what you can see is, you can always see the weight, which is the most important part. Now, let's see how this would work if we have more information. So instead of having 100 portfolios, let's make 25,000. And instead of having only these companies, let's add EA Sports, let's add Activision, let's add Goldman Sachs, let's add Amazon. So 1, 2, 3, 4, 5, 6, and let's add Coca-Cola. So we have 7 companies, we have a risk-free rate of 0, and as you move forward, this is the only part that you will make all the changes. So you can add here a comment user inputs, and this would be the part, the returns calculation, or the changes, daily changes. Now we can run this, and there is nothing that we need to change in the rest of the code. In fact, this is the only thing that we need to change. Now, well, I just said what I just said again. Anyway, one thing that you need to note, and what I did here on purpose, is you need to go to the most, let's say, time-consuming part of the script, but also probably memory consumption, is this for loop. Because what we're doing now is we're iterating through this loop 25,000 times. And the question is there something here that it's not really necessary to be run 25,000 times? Now, do we need to create weights 25,000 times? Absolutely. So for this part, there's not much we can do. We can add this into, actually no, this is actually quite okay. So we can maybe add it into one line, but there's not much we can do to improve the speed. We are adding it into the list, so that's fine. But what about this part, when we're calculating the covariance, or when we can hear the mean? Well, these are things that we can calculate and have them outside of our for loop and then reference to that variable that we already have. So this is just something that I would like to suggest. I left it here on purpose as a learning point, because in the past I didn't do it that way. And I think it's a good point to keep in mind if you're creating, actually for any for loop, just think of, is there something that I don't have to iterate over X amount of times? It would add to your speed. The risk-free rate, that's something that we already covered to some extent. And let's see what happens with our portfolio of these 7 companies. You can also change everything that when it comes to the visualization, it's really flexible. I have a separate tutorial on matplotlib if you want to learn more about that. So this is how it looks like at the moment. So what we have is the following. We have the risk is 0.17. If you remember in the previous iteration, we had about 0.3. So by adding more companies, we've managed to reduce our risk. And also our, let's say, of course, our weights are completely different. We have, and this is also maybe a good exercise for thinking of, all right, so what are the companies that we would have the most of in terms of value in our portfolio? Well, in this case, it's 55% in Coca-Cola, which seems to be the safest or the least volatile of all the others, which is indeed the case. If you want to achieve the highest return, then you will be investing a lot in Tesla, almost 63, a bit over 63%. And there is not really another one that stands out that much. Maybe EA is the next one with 11%, but still nothing comes that close. So what you're looking for is you need to, first of all, it solves your question, what is the optimal weights for achieving a particular goal? So what is the optimal portfolio for highest return, lowest risk, or highest Sharpe ratio? Here the ratio is 1.35. If you remember in the previous example, it was a bit over 1. So we've managed to increase the expected return compared to the risk that we're taking. Of course, the weight is different, and we have this visualization, and you can, of course, make sure that the font looks as you want. I just wanted to show you how you can change that. We have the returns on one side, we have the volatility on the other side measured by the standard deviation. We have the Sharpe ratio, so it's clearly that these are the companies that you would like to be in if you want to have the best Sharpe ratios, or the yellow parts. If you want to have the lowest risk, you can already see what is the allocation to do. If you want the highest return, you already have that. That's probably this point here at somewhere around 44, 45. So that's how at least you can read it. And again, it's important to take a look into this code and also think of improvement points. Maybe you would not want to print it this way. Is this the best practice? Absolutely not. You'd like to have a nice interface. Maybe allow the user to have these inputs as something that he can change, or she, and then the output would be a visualization with the basically this output in a much nicer way. But for the tutorial purposes, I think this is quite enough. If you have any questions or comments, please let me know in the comment section below, and I'll see you in the next one.